Good evening. Mars comes through opposition on the 22nd of May and is attracting a lot of attention among amateur astronomers at the moment. Mars is being explored by a robotic spacecraft, and the red planet offers observers the unique opportunity to view large surface features along with the changing size of the polar caps. Both the volcano Olympus Mons and the impact region known as the Hellas Basin are visible in moderate-sized telescopes, so now is a good time to take a look at what space scientists have learned about Mars over the last 54 years and whether we are any closer to discovering life on the red planet. The latest spacecraft to travel to Mars, the European Space Agency's ExoMars probe, was launched on the 15th of March 2016 from Baikonur on a 6-month journey to study the Martian atmosphere. It will be looking for a concentration of methane in various areas of the planet, which is a telltale sign of life on Mars today. So, exciting times lie ahead. The planet Mars has been known since ancient times. It was seen as one of the bright, wandering stars that slowly changed their positions through the zodiacal constellations. The planet has a distinct reddish hue, which the ancient Greeks determined represents the physical or violent, untamed aspect of war. Mars is therefore named after Ares, which, when translated, literally means battle, and Ares is the Greek god of war. Our solar system is made up of the Sun in the center, and in order of distance we have the rocky planets Mercury, Venus, Earth and Mars. Mars is 4,220 miles in diameter, making it 3,500 miles smaller than the Earth, and it lies at a mean distance of 141,637,000 miles from the Sun. The planet, therefore, moves around the Sun with less speed than the Earth, taking about 687 Earth days to complete its orbital path. The Martian year is therefore just over twice that of our own, so Mars does not return to opposition every year. It will next be at opposition on the 27th of July 2018. When seen in the night sky and the planet is near perihelion, Mars can reach magnitude minus 2.8 at opposition when it is due south of midnight and is best placed for observation. It then looks like a bright reddish star. It lies in the constellation of Scorpius, the Scorpion, above the bright orange star Antares, which in past times was known as the rival of Mars because it is of the same colour and of similar brightness. Not all oppositions are equally favourable. In 2018, Mars comes to opposition when it is near perihelion, and so the minimum distance from the Earth will be less than 35 million miles. At the next aphelion opposition, in January 22-25, the distance will be over 63 million miles. The difference in the orbital velocity of the Earth and Mars causes the red planet to appear to perform a loop amongst the stars that make up the constellations. This year, between the 3rd of March 2016 and the 22nd of August, the red planet will do just that. And you can follow its journey with the unaided eye by plotting its position every night against the stars of Libra, the scales, and Scorpius, the scorpion, using a star chart. This graphic shows what is happening. The outer planets move more slowly than the Earth, so our planet will catch up with Mars on the 17th of April 2016, and the planet will appear stationary in the sky. The Earth, which is the faster of the two worlds, then overtakes Mars, and in the sky, Mars appears to perform a loop, retrograding across the sky into Libra, where once again Mars is stationary on the 30th of June. Our Earth then lags behind Mars in its orbit, and in the sky, Mars again moves forward along its celestial path into the adjacent constellation of Scorpius. All of the other outer planets do the same, except on longer time periods. The polar axis of Mars is tilted by 25 degrees, so currently the position of the planet's celestial pole lies close to the bright star Deneb Alpha Cygni in the celestial swan. Mars rotates on its axis in 24 hours, 37 minutes, 22.65 seconds, so a day on Mars lasts 41 minutes longer than a day here on Earth. Astronomers call a day on Mars a sol. Since there is little difference between the Earth's day and a Mars sol, we can draw up a calendar showing the seasons on Mars, as shown here. We know that Mars takes 687 Earth days to travel once around the Sun. Therefore, southern summer, northern winter, lasts 160 Earth days, while southern autumn, that's northern spring, lasts 199 days. This is because Mars travels faster along its orbital path as it travels through perihelion, the closest point to the Sun. Today, it is summer in the southern hemisphere on Mars, and the autumn season will begin on the 4th of July. The escape velocity on the surface of Mars is 3.1 miles a second, which is less than half that here on the Earth's surface, where it is 7 miles a second. This is because Mars is smaller than our planet and there is less gravity on its surface. A 65-kilogram man would weigh 24 kilograms on Mars. The orange appearance of the Martian surface is caused by iron oxide or rust, while other common surface colours include golden, brown, tan and greenish, depending on the minerals being present. An astronaut would also need a spacesuit to survive because the Martian atmosphere is very feeble. The atmospheric pressure is only around 7 millibars as compared to more than 1,000 here on Earth. This is the same as if you were 15 miles above the Earth's surface. Passenger planes cruise at a height of about 8 miles and has to be pressurized, so the Martian atmosphere is very tenuous indeed. The main component is carbon dioxide, 95%, with nitrogen, 2.7%, and argon, 1.6%, along with trace elements including oxygen, water vapor, and neon. The Martian lower atmosphere, which extends up to an altitude of 28 miles, is influenced by heat exchange with the ground and is strongly heated by dust, which absorbs incoming radiation from the Sun. The dust can locally reverse the decrease in temperature with height, causing areas of stability, but its amount may vary seasonally and regionally. The mesosphere extends from 28 miles to 68 miles. The NASA spacecraft Pathfinder in 1997 detected a temperature minimum of 92 Kelvin. That's minus 181 degrees centigrade at an altitude of 50 miles, where carbon dioxide is predicted to condense as high-altitude clouds. There is also a temperature inversion lower in the atmosphere between 6 and 10 miles in altitude, where the temperature falls from minus 73 degrees centigrade to 92 degrees, which is believed to mark the height at which water ice clouds form. This graphic compares the Martian atmosphere with that of the Earth, Venus, and Titan, bottom right, which is the largest of the moons of Saturn. They show the variations in height and the absorption of heat radiation caused by greenhouse gases. Because of the atmosphere's low mass, seasonal temperature variations follow the point directly below the Sun quite closely. As a result, polar temperatures in the winter hemisphere, where the Sun is below the horizon for long periods, drop rapidly. The temperature drop is halted only when it reaches the condensation point of carbon dioxide. That's minus 125 degrees centigrade at 6 millibars of pressure. This means that a large fraction of the atmosphere condenses out into the polar caps and the latent heat of crystallization is released. The total amount of water vapor in the Martian atmosphere is equivalent to 10 square miles of water ice, comparable to the water content of the Earth's atmosphere. Our atmosphere contains the equivalent of 8,000 square miles. the difference being that the relative humidity of the Earth's stratosphere is rather low, whereas the Martian atmosphere is always near saturation. The mass of Mars corresponds to 11% of the Earth's mass, and analysis of the planet's volume provides a mean density of 8,670 pounds a square metre of the Martian surface. This confirms that Mars is a rocky planet with a small iron-rich core. Until recently, evidence relating to the core of Mars has been difficult to interpret and subject to large uncertainties. Over the last 15 years, a wealth of data on the planet's surface relating to its magnetism and its rotation has altered our picture of the Martian interior. It is now clear that Mars has a completely molten metallic core with a radius of 11 miles containing a large amount of sulfur, about 16% by weight. The average thickness of the crust on Mars is about 31 miles, with a maximum thickness of 78 miles. Earth's crust, averaging 25 miles, is only 1/3 as thick as Mars, relative to the size of the two planets. The main difference is that Mars has a dual crustal thickness, with the southern hemisphere possessing a thicker crust and the northern hemisphere possessing a thinner crust. The thicker crust of the southern hemisphere thins towards the crust of the northern hemisphere, so that there is an overall planetary mass redistribution to one side of the planet. Mars is accompanied by two small moons discovered by the American astronomer Asaph Hall in 1877, named Phobos and Deimos. In translation, their names literally mean fear and terror. Phobos is the largest and innermost of the moons. It has a very irregular shape with a size of 18 by 7 by 6 miles. The moon has a mass of 1,900 grams, about 1,200 pounds a square metre. This low density suggests that Phobos is either very porous, perhaps with large amounts of ice in its interior, or is a rubble pile object similar to the many asteroids, where the solid pieces are weakly held together by the moon's gravity. Phobos orbits around Mars 5,824 miles above the Martian surface. At this distance, it takes Phobos 7 hours 49 minutes to orbit around Mars, so Phobos makes almost 3 complete orbits during one Martian sol, which is at an angle of 1 degree. Phobos is in synchronous rotation around Mars, so its sidereal period is the same as its orbital period. Because Phobos orbits faster than Mars rotates, tidal interactions between Phobos and Mars are stealing energy from Phobos's orbit. As a result, the moon is slowly spiraling inwards towards Mars at a rate of 2 centimeters a year. In about 50 million years' time, Phobos will either impact the surface of Mars or be torn apart into a ring system as it passes through what planetary scientists call the Roche limit. Phobos is a very dark world. The moon is very heavily cratered, indicating that no internal geologic activity has occurred since its formation. Phobos also displays many grooves, up to 13 miles long, across its surface, which could be the surface impressions of deeper fractures associated with the porous interior of the moon. Many of these grooves are near the crater Stickney, indicating that the formation of this large crater violently shook and stressed the moon, creating new fractures and widening pre-existing ones. Large blocks of ejected material during crater formation can also be seen on the surface of Phobos, which occurred after the formation of Stickney. Diomas is the smaller and more distant of the two Martian moons. Like Phobos, it is irregular in shape, with a size of 5 by 1 by 4 miles. The density of Diomas is 1,750 kilograms, almost 4,000 pounds a square metre, suggesting another porous rubble pile body just like Phobos. Diomas orbits around Mars at a distance of 14,570 miles, giving it an orbital period of 1¼ days. The orbit is close to circular, with an inclination of 1.8 degrees. Like Phobos, Diomas is also in synchronous rotation as it orbits around Mars. Diomas orbits Mars at a distance of 14,570 miles. Diomas is another very dark moon and also displays a heavily cratered surface, but the surface is much gentler than that of Phobos, where craters and grooves appear relatively sharp. Diomas's subdued appearance results from a thick crust or layer covering the surface. This surface is composed of a fragmented material produced by impact cratering on the Moon. Mars has been visited by numerous space probes over the years, including NASA's Mars Global Surveyor of 2007, which have studied Mars in great detail. Thousands of high-resolution photographs have been taken to map the planet's entire surface, and science instruments have allowed scientists to study Mars in different wavelengths. From the Earth, Mars is a difficult planet to observe because of its small angular size. At opposition in 2016, it will be 18.3 arcseconds in diameter, so a telescope of at least 20 centimeters, that's 8 inches, is needed to be able to do useful work, which includes astronomical photography. One point to bear in mind is that astronomical telescopes turn the view of Mars upside down. Here is a view of the surface features visible from the Earth, with the North Pole uppermost. The Hellas Basin is very prominent and lies above the most famous feature visible on Mars, the dark triangular-shaped Syrtis Major. It used to be known as the Hourglass Sea, which is quite nice. Over to the left, Pharsis marks the location of the Martian volcanoes, the largest of which, Olympus Mons, is visible in amateur-sized telescopes. Nearby are Lunar Planium and Xanthi, which is the site of the Valles Marianaris, a huge chasm on the surface of Mars. Valles Marianaris is named after the Mariner 9 Mars orbiter of 1972, which discovered it. It is a system of canyons that runs along the Martian surface. At more than 2,500 miles long, 120 miles wide, and up to 23,000 feet deep, the Valles Marianaris rift system is one of the largest canyons in the solar system. To better understand the surface geology of Mars, let us take a closer look at these features using the science instruments on board NASA and European space probes.
A fleet of robotic spacecraft is exploring the Red Planet, and scientists are finding new ways to mine an ever-growing mountain of data. Satellites always orbit a planet's center of mass, but they can be pulled slightly off course by the gravity of massive features like Olympus Mons, the solar system's tallest peak. Now, a team of scientists at NASA's Goddard Space Flight Center has used small fluctuations in the orbital data of 3 spacecraft to map the gravity field of Mars. In this new map, low-gravity canyons like Valles Marineris in blue stand out from the high-gravity reds and whites of the Tharsis Mountains. By comparing gravity with topography, the scientists made an improved estimate for the crustal thickness of Mars, shedding light on its geologic history and confirming earlier indications that the planet has a molten outer core. The orbital data also revealed seasonal variations in the mass of the polar caps, showing that up to 4 trillion tons of carbon dioxide cycle annually between the poles. The new gravity map should prove useful to future missions as well, by allowing spacecraft to enter orbit more precisely, thus ensuring that the Mars fleet continues to return a massive trove of data.
On the surface of a moon or a planet, surface material made up of volcanic rock, like basalt, are more massive and are heavier than rocks of a sedimentary nature, like sandstone. On this map of Mars, the highest gravity areas are shown in red, followed by orange and yellow, with the lowest density mascons in blue. Straight away, you can see that the highest rated gravity fields are concentrated in the Tharsis area, middle left, where we also find the largest of the volcanoes on the Martian surface. The Valles Marineris region nearby is mostly of a very low concentration gravity field, shown in blue, which is to be expected, while the yellow band across the centre of Mars is of mean density mascons. The real surprise is a red mascon on the Martian equator, 100 degrees longitude, which actually lies at the centre of the Isidis Planitia, to the right of the famous Syrtis Major feature. It is 930 miles in diameter and is often described as the third biggest obvious impact structure on the planet, after the Hallis and Argaea basins. However, in my opinion, this high mascon signature seems to indicate that at some time in the past this was an active volcano which erupted, filling the area with lava. If it is a large impact crater, then the meteorite that created it is the cause of its high gravity concentration. I think that's unlikely because of its obvious immense size. To the left of Isidis Planitia is the Martian volcano Acraeus Mons. The large green oval area to the lower right, which is centered at 70 degrees longitude, is the Hellas Planitia. Hellas is the third largest impact crater on Mars. The basin floor is about 23,500 feet deep and extends about 1,400 miles east to west. Next, let us take a look at the local magnetic field of the surface of Mars, again from the data collected by the Mars Global Surveyor spacecraft. Areas of positive polarity are shown in red, and negative polarity is in blue. Broad bands of opposing polarity dominate the southern highlands. The globe shown here is centered on the south polar region of Mars, which shows that the bands of opposite polarity form concentric rings around the South Pole. Planetary scientists now believe that the cause is due to the convection of magma under the Martian surface. This plume of magma contributes magnetic activity to the thickening of the southern hemisphere of the crust. The removal of heat by this plume sets up a sufficiently large thermal gradient in the liquid metal core, causing convection, which in turn creates a magnetic dynamo. Shown in this graphic from left to right, a strong core dipole field imposes remnant magnetism, shown in red, upon igneous rocks intruded as a result of the mantle plume. When the field undergoes a polarity reversal, the reverse field is preserved in fresh igneous rocks, shown in blue. The polarity reversals continue, creating alternate bands of normal and reversed remnant magnetism concentric to the plume head. As the heat is lost from the Martian interior, the plume dies and the core dynamo then fades away. For the emergence of life, water is an important ingredient, and we now know that a lot of running water existed on Mars in the distant past, which has since been lost to space, while some traces remain beneath the Martian surface. This coloured graphic of Mars, made with data from NASA's Mars Global Surveyor, shows the extent of water locked up in the Martian surface. The highest concentrations are shown in blue, which is mostly found in the tropics of Mars, from the latitudes of 60 degrees, with the highest levels reserved for the polar regions. This is to be expected because the polar ice caps of Mars are composed of solid carbon dioxide and water, and they grow and shrink with the Martian seasons, just like the Earth's polar ice caps. From the same data, it is possible to determine the positions of the edges of ancient lake beds and Martian coastlines. Take a look at this graphic. On the left, we see the extent of the oceans that lie roughly at the boundary between the uplands, green, yellow and red in this laser map, and the low-lying areas, light and dark blue. Other schemes envisage a much more restricted ocean, and imagery suggests that some of the shorelines features are in fact wrinkled ridges. The view on the right shows the areas on the Martian surface whose material is a very poor conductor of electric current, as determined by the MARSIS instrument on board ESA's Mars Express spacecraft. The smaller values observed in the deposits of the northern lowlands are interpreted as low-density sediments and ice, which is consistent with the presence of an ancient ocean. Looking to the future, NASA's InSight mission has finally been given the green light to launch to the Red Planet in 2018. It will help improve our understanding of the processes that shaped the rocky planets of the inner solar system more than 4 billion years ago, and it will help improve our understanding of the geology on Mars.
InSight isn't just a Mars mission, it's really a mission to the terrestrial planet interiors.
The rocky planets, or we call them terrestrial planets, are the small planets of the inner solar system that are a lot like the Earth. So Mars is kind of the Goldilocks planets. It's not too big, it's not too small, it's just right. If it was too big, it would have retained a lot of activity and erased all the evidence that we're looking for. If it was too small, it never would have undergone the same processes that form the Earth, and so it's really just right.
Mars will give us this insight into early planet formation and early planetary processes.
Understanding the details of the structure of the interior of Mars will allow us to address questions of planetary formation that we've only been able to guess at before.
We are missing cold, hard data, and this is what this mission will provide.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
It's going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed. And what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be in composition.
The Lockheed Martin flight system, our role is to build the aeroshell, the cruise stage, and the lander. All three of those have extremely high heritage from Phoenix.
20 meters, 50 meters, standing by for touchdown. Touchdown signal detected. Landing it sequence initiated.
This deck is the same Mars 01 lander deck. In fact, we use this in the test bed on Phoenix. So it will be reconfigured for InSight because we have different instruments. We have the wind and thermal shield, the seismometer, and the heat probe. But other than that, it's basically the same deck.
It's an advantage for us to use heritage designs because we're familiar with them, we've tested them, we've qualified them, they worked successfully on the surface of Mars. We have a really big head start.
A lot of things have come together to make it possible to learn a great deal about the interior of Mars from a seismometer. We used to think we needed 4, 10 stations on Mars, but we know that we'll be able to get a lot of that same information from a single station.
So we have Kinéis that's building our seismometer that's been under development for many, many years. And we're fully confident that they're going to be able to deliver a quality product on schedule.
InSight will be the first mission to deploy a geophysical observatory on Mars. About 40 years after Viking, it will reopen the case of Mars seismology.
What it does is it just sits on the surface of Mars, and it's like a stethoscope. It listens to what's going on inside Mars.
We will cover really all the seismic bandwidths. We will be able, with this signal, to get information on the interior of the planet.
On the HP Cubed instrument, we have that being delivered to us from DLR. That also has been under development for many years.
And what this probe does is it penetrates into the subsurface up to 5 meters. On its way, it measures the thermal conductivity.
We're very comfortable with all the testing that we've done to show that the mole can actually penetrate through the Mars regolith and get into the surface. We have a test bed that we've set up. We've run multiple different types of tests through different types of material to gain confidence in our ability to penetrate to the level that we need to penetrate to get our science return.
The basic mantra of our flight system design is low risk, and with that is low cost risk.
We've been to Mars before with the JPL Lockheed Martin team. We've been to the surface of Mars before successfully with Phoenix. We know how to operate the arm. The surface operations are much, much simpler than Phoenix. We're putting 2 instruments on the surface and then we're leaving them there with no ground in the loop interaction, repetitive weekly uplink downlink sessions. We're just made to do this mission.
The heritage for InSight extends way past just the flight system and the hardware. It extends to the personnel, the processes, the tools that we've developed, and so forth.
With one spacecraft on a Discovery budget, we're really going to be able to do the science that for the last 20 years we thought would cost at least $1 billion to $1.5 billion and require 3 or 4 spacecraft.
We have very robust margins built into InSight. 50% margin on our instrument deployment timeline. We have 50% margin on our science data collection. We have 500% margin on our daily data volume. We're in good shape. It's going to be a great mission.
There is a good chance that there is life on Mars. It may not take the form of plant life or creatures roaming the surface. It will most likely take the form of single-celled microbes, and the excess of the gas methane in distinct areas of Mars will help us find it. These lovely illustrations, drawn by Sir Patrick Moore's mother, Gertrude, sees the Martians as adorable creatures. I wonder, is there life on Mars? We will just have to wait for the official announcement. Hopefully, we will know before man first steps foot on the Martian surface around 20 years from now. That is all we have time for this month. Please visit our website, Astronomy in Space Blogspot, where you can watch all of our past shows. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, Good evening.